Great to see you here. In the previous series of videos, I was talking about mathematical induction. So basically, we were trying to prove certain statements using the principle of mathematical induction. Now, in certain cases, mathematical induction is not strong enough. It's not enough to prove certain statements. And we have to introduce what we call strong induction. Now, let's have a look at the strong induction. What is it about? And how can we compare it with the mathematical induction? When we looked at the mathematical induction, we considered a basis step for which we prove that P of 1, a certain statement for the initial value, is true. And then we try to prove the induction step, the inductive hypothesis, where we would like to prove that for all positive integers k, that when P of k is true, then P of k plus 1 is true too. Now it means we try to find a statement, we have that hypothesis, and we try to find out if we know that P of k or assume that P of k is true, can we use that inductive hypothesis to prove that P of k plus 1 is true. Now in some cases it's not sufficient, and then we go to strong induction. And strong induction is in fact when we are not just looking for P of k and then conclude that P of k plus 1 is true, but we're going to look at P of j, and j is in fact an integer starting from 1 up to 2 up to k, and when we can conclude that P of j is true for all values of j, then we will conclude that P of k plus 1 is true. Now let's have a look at the principle again. The strong induction means in fact that to prove that P of n is true for all positive integers n, where P of n is a propositional function, we have to complete two steps. The basis step is still the same. We verify that the proposition P of 1 is true. And then we are going to look at the inductive step. And for the inductive step, we have to verify that the conditional statement or the inductive hypothesis is true for P of 1 and P of 2 and P of k before we can conclude that P of k plus 1 is true for all positive integers. So here we do not just take one step, we have to look at more steps. Now, when we look at the infinite staircase, and in the infinite staircase, or the problem of the infinite staircase, we have proven with the mathematical induction that when we can reach the first and the second step of an infinite staircase, then we know we can reach any step and of that staircase. But what we want to know now is a little bit more. It means if I can reach the first and the second step, can I reach two steps higher? And we try to prove this using the classical method of the mathematical induction. The basis step is true. We can reach the first step of the staircase. So basically the basis step is true. That's already proven. And now we have to look at the inductive step. And when we look at the inductive step, is in fact, it means if I reach a step, can I reach two steps higher? And we want to prove if we can reach the kth step, can we also reach the k plus first step? Now, we cannot complete the inductive step because we only know when we can reach the k step, we can reach the step two higher. There is no information about that in the total mathematical induction proof. We cannot prove this. So basically, we are having some elements that are missing. So we cannot prove this. Although it sounds very easy to prove, if I can reach one step, I can also reach two steps higher. But in the typical classical mathematical induction, I can only prove that if I can reach a step, I can reach one step higher. Now let's see how this translates in the field of the strong induction. We look at the infinite staircase. Let's say we can reach the first and the second step of an infinite staircase. We can reach a step. Then we can reach two steps higher. Basically, we have the same thing we want to prove, but instead of using the mathematical induction, we're going to use the principle of strong induction. Basically, we have to prove every intermediate step. So let's now have a look at the proof using the strong induction. The basis step is still the same. We can reach the first step of the staircase. This is true. It is possible to reach the first step of the staircase. We go to the staircase, we are there, we can reach that first step. So P of 1 is true. Now we look at the inductive step. And the inductive hypothesis states that we can reach the first case steps of the staircase. We will prove by strong induction that this hypothesis is true. Let's say when we can reach the first k steps, we can also reach the k plus fourth step. But we have to prove that for all the intermediate steps. Now, we already know that we can reach the second step. Now we can conclude for k larger or equal than 2, we can reach the k plus fourth step from the k minus first step, because we can climb 2 steps from each step, and we can reach, and because k minus 1 is smaller than k, we can prove by the inductive hypothesis that it is possible to reach the k minus first step. So basically, using the strong induction, by the fact that we can use those intermediate steps, that we look at P of all those intermediate steps, we can also prove that when we reach the k minus first step, we can also reach the k plus first step, which is 2 steps ahead. So the strong induction in this case proves that this statement is true. And this would not have been possible to prove using the classical mathematical induction. Now that's the introduction to the strong induction. And of course, we're going to look into some more examples of proofs where we are using strong induction to conclude or to prove certain statements. You're doing a great job, and I'm looking forward to seeing you at the next presentation. Thank you, and bye-bye.